Hi team, welcome to Wiggins Maths. In this video we're going to be having a look at geometric series. Okay, so first of all, do not neglect the formula booklet. There's some really useful stuff in there, particularly in this topic for arithmetic series and geometric series. Okay, so just like with an arithmetic series, we could be asked to prove a geometric series. And this is a slightly different approach. I mean, it's almost a little bit strange, it's almost a little bit quirky. It's certainly something that I would suggest you practice. Okay, so the sum, and then it's adding all of the terms together for this geometric progression, isn't it? So it's A, add A, R, add A, R squared, add, and then the nth term, if you remember, is AR to the power of n subtract 1. Now, we're not going to reverse it like the arithmetic series. What we're going to do is we're going to multiply both sides by r, which you may think is a little strange, but just go with it. Okay, so now we're going to subtract those two things from each other, and something magical happens. So Sn subtract r lots of the sum. Notice when we subtract, they cancel, they cancel, they cancel, leaving us with just A subtract AR to the power of n. Now we're going to factorise both sides. So here we're going to take out a factor of Sn, which is 1 subtract r. Here we're going to take a factor of A out, which is 1 subtract r to the n. And there we have it. And of course this is only true if r is not equal to 1. In which case it wouldn't be a geometric series anyway, right? You just repeat the same term over and over and over again. Okay, so that's the proof. Okay, so the third term of a geometric sequence is 324, the sixth term is 96. Show that the common ratio is 2/3. Now, show means you have to show, it means you can't use. So U3 is AR squared. The sixth term, U6, is AR to the power of 5, that is 96. Divide both terms, and you will get r cubed equals 96 over 324. Now I suspect 96 over 324 is something a little bit nicer, and indeed it is. And then if you cube root that, you do in fact get 2/3. We've successfully shown that the common ratio is 2/3. Okay, find the value of A. So part B, I'm just going to use one of those expressions. So we're going to get A, and that's equal to 324. So if I do 324 divided by 2/3 squared, I get 729. So A is 729. And then find the sum of the first 15 terms. So S15 is A 1 subtract r to the n over 1 subtract r, which is what we just proved in the previous example. We've got A, we've got r, we've got n. So it's a case of just plugging these things in. So 729, 1 subtract 2/3 to the power of 15 over 1 subtract 2/3. And you have to be super careful when you're typing this in. Don't make any silly errors. It's very easy to do so. So really take your time. Make sure it's all typed in perfectly. Okay, and it is 2182.005639 and so on. It's not been told to round it to anything, so I think that will do. Lovely. So similar again, previous sorts of questions. We want the value to exceed 1.5 million, so the sum. So this determines that it's a series, not a sequence. So we want Sn to be greater than 1.5 million. Okay, so that is A 1 subtract r to the n over 1 subtract r is greater than 1, 5, 0, 0, 0, 0, 0. So let's just plug in what we know. We know A is 1, we know R is 2, and N is what we're trying to work out. So hopefully we can see it's a very similar type of problem to before. So it's 1 subtract 2 to the power of N all over 1 subtract 2. So first thing I'm going to do is I'm going to multiply both sides by -1. Now remember what happens when I multiply by a negative, it's going to reverse the inequality, isn't it? So that's going to be negative 1.5 million. Okay. So now I'm going to multiply, I'm going to subtract 1 from both sides. So that should be a 1 on the end. Okay, and now I'm going to multiply both sides by -1 again, which means it's going to, oh sorry, I didn't reverse it there, did I? Silly me. And then I've got to make sure I reverse it again here. And then the last job is I'm going to take logarithms. So actually I'm going to take log in base 2 in this example, because then I don't have to deal with anything on this side. So on log base 2 of 2 is greater than log in base 2 of that. So that's going to be n is greater than, and then type it to my calculator, log in base 2 of 1,500,001, which is 20.5165 and so on. So n must be 21 in order to get the series to sum to something greater than 1.5 million. Lovely. As always, just by watching this video doesn't mean you'll instantly be able to do it. Practice is the key to success, and it will make you better and better and better. And of course, as always, amateurs call it genius, masters call it practice.